Last couple of videos we looked at how the Julia sets and the Mandelbrot set images are generated. Among other amazing properties, these objects are what we call fractals. A completely mathematical definition of what a fractal is does not exist, but the most distinguishing qualitative characteristic is that fractals exhibit self-similarity at different scales. This basically means that you can identify some pattern which you can find at many, in fact it should be infinitely many, different sizes. For example, the Mandelbrot set is a fractal because you can find smaller Mandelbrot set looking things inside it. So for example, when I zoom in here on the random region, you can find a smaller Mandelbrot set looking thing. In fact, I can find infinitely many of them. They do not have to look exactly as the original object, but at least they should be approximately similar. So because we can find some pattern at infinitely many different scales inside this object, we call it a fractal. Similarly, most of the Julia sets are also fractals. So for example, here I can identify this squiggly looking thing, and I can find that squiggly looking thing inside infinitely many times. But actually, the Mandelbrot set and the Julia sets are what I would call fancy fractals. The truth is that people have been playing around with fractals for a very long time, and there are many examples that are much simpler to generate. So this is an example of a very well-known fractal called the Sierpinski triangle. As you can see, the Sierpinski triangle is made up of other Sierpinski triangles of smaller size. The pattern continues on forever. Mathematically, the Sierpinski triangle is most easily defined using what's called an L system. Simply put, in an L system you first define your base shape, and then you give what's called the generator rule. The idea is that you start with your base and then apply the generator rule infinitely many times to get to your final shape. In case of the Sierpinski triangle, the base is a black triangle, and the generator rule is, whenever you see a black triangle, replace it with this. Do this infinite number of times and the result is the Sierpinski triangle. The fun thing about being a mathematician, of course, is that you need not carry out this procedure explicitly. That would take you an infinite amount of time. Instead, you can simply consider the result and entertain the consequences. In this video, I would like to entertain some of the consequences of this funny looking fractal. It is called the Koch Snowflake. The base of this fractal are three lines arranged in a triangle, and the generator rule is, whenever you see a line, replace it with this. In other words, you grow a little bump right in the middle of it, where this indent forms an equilateral triangle. So basically all of these little line segments here are of the same length. The Koch Snowflake is then defined as the result of applying this procedure infinitely many times. So what is one of the interesting consequences of this shape? Well, let's try to calculate the perimeter of this object. It is not immediately clear on how one would go about doing this, but basically here's what we are going to do. We will proceed iteratively. To generate the Koch Snowflake, we start with the base and apply the generator rule infinitely many times. So let's say the base was a triangle with sides of length 1. Well, then it is easy to see that the base had perimeter 3. Now, when we apply the generator rule a single time, what is the new perimeter? Well, every one of the original line segments now looks like this. So we have grown a little equilateral triangle in here. Now, since the original length here was 1, it is easy to see that every one of these tiny segments must have length 1/3. So the total length here must be 4 times 1/3, or 4/3. And this shape contains 3 of them because there were exactly 3 original line segments, and every one of them now looks like this. So the total perimeter of this object after a single iteration is 3 times 4/3. Now let's take a look at what happens in the next iteration. Every one of the original line segments now looks like this. So basically what we have done here is we've taken this one and we have grown little bumps on them to get to here. Now the length here was 1/3, as we have seen here. And now when we grow a little bump here, and this bump is an equilateral triangle, it is easily seen that every one of these smaller tiny segments must have length 1/9. Therefore, the total length of this thing here must be 4/9, because there are 4 of them, and then there are 4 of that in here. So it's 4 times 4/9, 16/9. And in an entire shape, we have 3 of those because we have 3 original line segments, and every one of them now has length 16/9. So the total length here is 3 times 16/9, or 3 times 4/3 square. You can convince yourself that in the next iteration the perimeter will become 3 times 4 over 3 cubed, and 3 times 4 over 3 to the 4th, etc. Basically, the general formula for the perimeter is 3 times 4 over 3 to the n, where n is the iteration number. But the Koch snowflake is defined as the shape you get if you do this infinitely many times. So what then is the total perimeter of the Koch snowflake? But more mathematically, what is the limit of 3 times 4 over 3 to the n as n goes to infinity? So some of you may have guessed it, it's infinity. In other words, the perimeter of the Koch snowflake is infinite. Intuitively, this is because the Koch snowflake is sort of infinitely wiggly. However, the most amazing thing here is that the area of the Koch snowflake is finite. This is easy to see because you can enclose the Koch snowflake in a box of area 1 or 2. If you actually do the math, the actual area is about 0.7. So for me, the most interesting thing here is that the Koch snowflake is an example of a shape with finite size but an infinite perimeter. So this is just an example of some of the crazy properties of fractals. I didn't even start to get into some of the more mind-boggling things. For example, fractals like the Koch snowflake are not one-dimensional like lines, not two-dimensional like planes, but they have fractional dimension. For example, the Koch snowflake is about 1.26 dimensional. More on that maybe sometime later. I hope you find this interesting, and bye-bye.